Hi, I'm Michael Waldman. I'm a high school junior at NSU University School, and this is my entry for the Khan Academy Junior Breakthrough Challenge. And what I'm going to be covering is a fundamental concept of calculus. And calculus is just the study of how things change. And that's a pretty basic definition of it, but it gives you an idea of what it is for anyone that's not familiar with what it is. So there are two fundamental aspects to calculus. There is differentiation and there is integration. And these two undo each other. They are polar opposites in every respect. And that might make sense after, but for now, all we're going to be covering is differentiation, which is probably the most important thing to understand in calculus because it opens the gate for understanding for just about everything else, including integration, because it's much easier to understand integration once you understand what differentiation is. So let's get down to it. What is differentiation? Differentiation is finding a derivative, and if you're not familiar with calculus, that might not make a lot of sense either, but a derivative is just an instantaneous rate of change. Think about it as a slope, but at one point instead of two, because we know, for example, let's take the function x squared. We know that a function, we can typically find the slope just doing f of x2 minus f of x1 over x2 minus x1 delta y over delta x. They're all equal to each other. It doesn't matter who you define slope. Basically, it gives you the rate of change between 2 points. But for calculus, what we want to find is the rate of change at one point, which is the instantaneous rate of change. And I'm going to show you how you can intuitively understand how to find that, even though this is probably going to be a pretty lengthy way, and later on in calculus you'll learn there are much easier ways and much shorter ways in which you can come to find the derivative of something. But it's really important for you to understand. So let's take 1 point, and we want to know what the rate of change is at this point. We have no idea right now, and we'd like to find out. We have, again, the function, this is f of x equals x squared. So we have that function right here, and we want to find the rate of change here. Let's call this point x comma f of x. And let's call this point x plus h comma f of x plus h. And all the h is just the difference between here, which just means that this x plus h pushes that point a little bit more to the right, and thus makes it have a different y value. We're just saying it's farther off here to the right, a little bit greater than x. So we can find the slope between these 2 points. It just looks something a little bit like that. It'd be aligned, and we'd be happy because we have our slope, except it's between 2 points, and we need to find it at 1 point. So how could we do that? Well, if we want to find the slope between these 2 points, all we'd have to do is do f of x plus h minus f of x over x plus h minus x. That might seem a bit confusing, but remember, all we're doing is just finding the slope. We're taking our y value right here, we're subtracting our y value right here, and then we're taking the x value here, we're subtracting the x value here, and that's just written right over here. So all we're doing, again, if we want to simplify this, is just f of x plus h minus f of x over h. This x cancels out with this x, and we're left with this. This will essentially give us our slope between these 2 points, and that can apply to any function, but we don't want the slope again between 2 points. We need to find the slope between just at 1 point, and it's actually pretty simple how we're going to do that. So we obviously can't just try to plug in this point and hope that we can get an answer, because this takes in the slope equation takes in 4 different variables, but we can kind of try a little trick, and I'll show you how that's going to work. So if you have x and it's at a considerable distance from, if you have x plus h and it's at a considerable distance from x, then you're not going to have an accurate slope, because this is not a linear function that we're dealing with. It's an exponential function, which means that we can't just take a slope, because slope is a linear rate of change. So to give us an accurate representation of what any function that's not linear looks like, we need to find the instantaneous rate of change. Again, that's a derivative. So if we start making h smaller, this is the most important part in the entire concept to understand. If we start making h smaller, we're getting it closer to x. We have x plus h and we have x. We make h smaller. That means this gets closer and closer. We keep making h smaller and smaller. And notice the smaller h gets, the more accurate it seems to approach the point. So when you draw this out, this is getting a little messy, but essentially we want to make h so small that it will nearly be x. Remember, it can't be just x and x, because then that would fail, because we'd only have one point and we can't plug that in. So we want to make h as small as possible. In fact, we're going to have h approach 0. And don't get scared if you see a limit and you're not quite sure what that means. All we're saying here is that we want to see what the function is going to look like when h gets really, really small, when it gets really close to 0, and we're doing the same thing. So x plus h minus f of x over h. We have the same definition, and now we see a problem. If we have h come to 0, then we're dividing by 0, and that is a big no-no. But we can get past that. Let's try plugging in for the actual x squared function. Now, if we do that, we get x plus h squared minus x squared over h, because again, we are just plugging x plus h into the x squared function, because we have that value right here, again here, and then minus f of x, and f of x is just x squared all over h. H isn't changing for this situation. Now, if we actually multiply this out, we get x squared plus 2xh plus h squared minus x squared all over h. And this cancels out with this, and then we're left with 2xh plus h squared over h. Still looks a bit complicated, but now this cancels out with this. This cancels out also with this. Not that it matters, because remember, h is going to be 0. At that point, you're just left with 2x plus h, and the h beautifully goes away because it's becoming 0. And that means you are left with 2x. That is the limit as h approaches 0 of f of x plus h minus f of x over h for x squared. And do not think that this is going to be the derivative for every function, because remember that all functions are going to be different, which means that all functions are going to have different derivatives, and you would have to do the same process of doing x plus h, plugging that into the function minus f of x all over h, again for a different function, regardless of what it is, x cubed or 2x squared, it would be different because you have different values, and thus you're going to have a different rate of change at that point. But there are going to be much easier ways to do this that you're going to learn. But for now, what's important to understand is the process that's actually happening here is that we're taking the slope, we're kind of using a trick. We're making h really small to give us the most accurate approximation of what the slope is going to look like when it's just at one point. And the way we did that is just making h really small. So now, if we want to find the rate of change at any point, it's super easy to do. Say we want to find the rate of change at -4, 16. Not that the y matters. You don't need the y. You know that, and this is just notation for a derivative dy over dx is equal to 2x. We want to find it at -4. All we do is plug -4 into our 2x, and we have the answer. We know that our rate of change at -4 is equal to -8, because we plug in the 2, -4. That means that this is changing at a slope of -8, and you can draw it out so that it actually makes sense for you. This is approximately -8, maybe a little less, but remember, it's decreasing, and that's what this slope is showing you. It's showing you that it's decreasing by -8. If you get higher, you could actually look at how it's, if you go more towards the left, you could actually look at how it's decreasing at a higher rate. Same thing, you come here, you see there's zero change at 0 because you plug in 2 times 0. It's very cool how you can plug in all the different numbers and actually see how the function mimics that behavior. And that's the intricacies. Those are the intricacies and how amazing calculus is, because it lets you calculate instantaneous rate of change, basically using principles of algebra to find how things change at a time instead of having to be limited between kind of an average between 2 points. And I'd like to thank you for reviewing the submission and thank everyone for their time. And thank you for watching.